Thank you very much for the invitation. Thank you, Stefania. And I must add that I was here before. I'm now here for the second time, and that's one of the reasons why I immediately said yes when I got the invitation. So it's a wonderful place. And thanks also, actually, to the two speakers before me who introduced the subject, so that I am going along the same lines. Along modification of carbon nanotubes with several kinds of chemical reactions or other interactions. What we do is to fill carbon nanotubes, and we start with, from a very well-defined sample. We start from a very well-defined carbon nanotubes. The whole approach is a material science approach, and as all of us should be aware, but some are not, it is very important to characterize the materials and know exactly what we are talking about. So we start very well-defined, very good carbon nanotube samples with a relatively narrow diameter distribution. And we put in several kinds of molecules to the inside. So we had the first one, which is of course the C60 filled peapod. It was not us who did this first, but we were working on them a little bit. Then you can put in ferrocene, which has a much smaller diameter or molecular size, or you can put in coronene, which is again an aromatic hydrocarbon. And the next, what you can do, you can anneal them all, and what happens then will be that they will all fuse into an inner nanotube, and you will get a double-fold structure. Okay. Now, how can you prepare those samples? The first one was done in 2000 by Smith and Lodzi at Penn, and he did it just by subliming C60 into the nanotube. But you still can do, if you want to have, if you have more sensitive samples and you want to have a lower temperature, is that you do a so-called nano extraction from a solution, say with ethanol, any kind of solvent, which is have not very strong interaction with the gas molecule, but has a strong interaction with where the gas molecule has strong interaction with the nanotube. What you do is your nanotube is filled, this interaction is very strong, you have a strong van der Waals interaction here, and then the solution is always saturated, and you fill your whole tube. The problem is that when you have these filled nanotubes, you always have a little bit of solvent inside. And what you can do is use supercritical carbon dioxide. This is, you just make it kind of liquid. And you use very mild conditions. You don't have to go very high to the sublimation temperature. And then when you put it into the reactor and leave it there, and when you open your reactor, then your carbon dioxide vaporizes again and goes away, and you have no contamination inside the tube. So that's a good method for filling. What do we use for analysis? Of course, you want to know what's in your sample. We mainly use infrared spectroscopy. It's, or we also use visible and UV, and a few lines, laser lines for the Raman. You see that you have all kinds of activity, optical activity in the nanotubes in this region, so it's really good. And in the IR, you have the vibrational peaks of the gas molecules, and you can, in principle, identify them by that. Okay. The first question that you want to see is whether once you have done your reaction, whether your molecules are inside or outside. Obviously, microscopy is a very nice method for that, and these are done actually by our collaborator Andrei Klobistov at the University of Nottingham, and you can see all your sample before you wash it and after you clean the surface. You always have to very, very thoroughly clean the surface in order to try to have your hybrid structure and not have no contamination here. But the problem is you cannot send everything to a microscopy facility once you have your samples, because that would be too expensive and too time-consuming. So what we did was actually what we discovered by working with these samples was that if you do the if you do the Raman, you see the Raman spectroscopy, you see a tiny little peak from the molecules inside, And you can identify this actually by a little shift of the Raman frequency. So that tells you that you have molecules inside. But the same is for the UV spectra. You see them from the encapsulated molecules. But if you do your infrared, this is C60 infrared spectrum. This is your sample before washing. And this is the one after you washed it. And okay, we have now what we can deduct from it, that if you have a washed pea pod, then you have no ATR infrared signal, but you do have a UV and a Raman signal. But this is, okay, this is good for practical purposes, but we still didn't understand it, and we tried to see whether we see it with other systems as well. And so if you do the same with ferrocene, and now you have another method, you have the Mössbauer spectrum, because you have iron in the middle of the material, you see in your sample that you have a lot of ferrocene inside. Actually, it also tells you that you have exactly the same Mössbauer spectrum as ferrocene. That means that there is no charge transfer. This is not Coulombic interaction. This is definitely some kind of pi-pi interaction between the rings, the pentacene rings, and the walls of the nanotube. But, so you have something, you have ferrocene in your sample. But again, if you, before washing, you get these little peaks of ferrocene here, and after washing, you get, this is basically junk. It's just, the spectrum is blown up so much that you see all the contaminations and noise, but there is no peak of the ferrocene. Okay, try with chroinine, same thing. You have a little bit before you wash it, and you have basically nothing after, after washing. You don't see anything, nothing comes out from the inside of the nanotube in the infrared range. And this is very strange because, okay, let me get back for a moment. The material is fairly transparent in this range. This is not an explanation. Okay, so the explanation actually came from colleagues who did a method for the dipole image induction. And the explanation is that as soon as you have a dipole vibration here, you have an image dipole in the wall of the nanotube from the delocalized electrons, and your image charge will change, will move out of phase with your vibration and will cancel the vibration. That's a very, very nice explanation, and I think we have it all. But that also means that you can use this whole picture for something else. And this is when you have your organic molecule outside of the nanotube. And this will then give you a kind of selection rule now. Because what will happen is that in this case, you cancel everything. Because for every direction of dipole, you have something because of the cylindrical symmetry. You have an image dipole. But here, you only have an image dipole for the vibrations which are along the wall of the nanotube. And we could see this. Actually, these are several polyelectrolytes, polyaniline and polycarbazole on the surface of the nanotubes. You can see that some of the ring vibrations disappear. And in the case of polycarbazole, you also have a contrast because your counter ion, the perchlorate, which is isotropically distributed along the nanotubes, there doesn't lose intensity, but everything else does. So you can basically say also from these spectra how strong the interaction is between the nanotube surface and the gas molecule. So once we had all these tools in our hands, we wanted to use it for something, and we had a European project. This was called 5 Lumen, which recently closed. And this was about luminescent in confined media, basically encapsulating luminescent molecules in order to keep the luminescence and protect them from the environment. So that was the goal, and it was turned out that it's not so easy. In fact, this is the one example which is really, I think, the most beautiful, and this is from Maria Antoinetta Loy from Groningen University. She put in oligotyrosine systems into the nanotubes, and they could show that the luminescence remained. And it was exactly these two, the dashed and the full lines are just the original molecule and the encapsulated molecule. So what you see is exactly what you would expect from the molecular luminescence. They don't change very much, the characteristics of these. In contrast, there was another report which used to be very popular for a while, and this is now coronary molecules. I showed them before, but I will show it again. You put coronary molecules into the nanotubes, and they called it nanopringles because of the Pringle chips. And what happened there, what they showed was that the luminescence changed very much. It shows from blue to green. Now the proof these authors gave was the Raman spectrum, which was attributed to the coronary molecules inside, and photoluminescence, which changed a lot. You can see this. This is isolated coronary, and this was the predominant of the result. Okay, but the problem was that a few months later, another report appeared, where they also had the TM pictures and Raman spectra, and what was suggested here was that inside there are no nanopringles, but there is graphene nanoribbon formation, and of course it would be very, very exciting, because if you had these graphene nanoribbons inside, then you can just cut the nanotubes and take them out, and you have a nice, well-defined graphene nanoribbon. Now, okay, obviously these two reports were contradictory. What was the problem? Okay, first of all, we have, what happens is, what they do is they open the tubes, the ends of the tubes by just oxidation, then they sublime coronene, and then do a washing with toluene to get rid of the surface adsorbed molecules. And what you see in one TEM is very different from the other one. So this is not a very difficult procedure. We could do that, so we decided to undertake a study to see which parameters influence the process to arrive to such different results. And what we did was, okay, there was another actually contradiction in the Raman spectrum. This is that the Raman spectra are the same, and these are attributed in one paper to coronene and the other one to the graphene nanoribbons, which are basically the polymers of the coronene. Just one check is actually, it says that in the Raman here, there are too many peaks for it to be coronene. The coronene spectrum doesn't look like this. So we decided to have a series of coronene-filled nanotubes with different parameters. You see that one of the parameters is the sublimation temperature, where you form these hybrid structures. And so what we did first is basically we just took the spectra. Okay, we took the Raman spectra of the coronene, the first step of the graphene nanoribbon formation, which is the dimer, the dicoronylane, and we took the filled sample, and we compared them. Okay, that's very easy. What you have here is in your hybrid sample, this is obviously a dicoronylane molecule. Okay, so that's what you have here. Then, of course, we sent some of the samples to Nottingham for TEM, and what we could see is that in some samples you get these this column-like arrangement, but in others you get something like the polymerized type. Okay, and this also I'll come back to this, but the TEM image also depends on time, because you are giving a lot of extra energy by the electron beam, and that's already very important for this hydrocarbon, these organic molecules. But anyway, so what we did, okay, remember that we have the supercritical carbon dioxide method, and therefore we can have structures which are filled at under very, very mild conditions, where you cannot have polymerization at all. So this is a little bit complicated structure, but what we have is we made this filling at different temperatures, This is just a very, very mild condition. Now, this one is where this is sublimation, where you have already colorine sublimation, but you don't have dimerization temperature. The gas, you are below the gas phase dimerization temperature, and this is where you are above the polymerization temperature. What you can see is that at relatively low temperatures, you don't see anything in the Raman spectrum of the hybrids. But as soon as you get above a critical temperature, you have dichroronylane. And from the, actually, we've had a lot of experience in this, and from the intensity of the lines, we deducted that this cannot come from encapsulated molecules. You don't have this high intensity of encapsulated molecules. This must be on the surface of the nanotube. If you look at now at the photoluminescence, which we are interested in a suspension, then what you see is, again, you have basically nothing at the low temperature filled material, but you start have a little bit in the at the low temperature, and then when you get to a high temperature field, the same thing what shows the Raman here shows you is exactly the dichroronylane photoluminescence. And this is actually another structure which you can make. This is coronane nanocolumns. They are called coronane nanowires, and they are exactly what those nanopringles are without the nanotube. And those also show, obviously, a very different photoluminescence. So this probably cannot come from outside, from inside the nanotubes. So we know that also if you watch the nanotubes and you look at you analyze your filtrate, it shows you that the washing process cannot remove the dichroronylane. It removes the coronine, but not the dichroronylane. But we also know that our temperature is too low for vapor phase dimerization. And nevertheless, the question arises whether your material is only inside. And what we thought was that it isn't inside, it must be outside, and it forms because of what we call templated oligomerization. Your graphitic surface catalyzes the polymerization of the coronine. So we took a little more of control experiments, and we used Comocat nanotubes, which Professor Lanzari already introduced. So you know that these are too small for the coronines to go inside. We have graphite, which is a flat surface. You cannot have obviously anything inside. And we wanted to see, then we have our single wall and multiple nanotubes, and we wanted to know if we have anything different in the hybrids. And what we see is that we basically have the same Raman spectrum on the graphite and the 0.9, the Comocat nanotubes, as with everything else. And you also have the suspension photoluminescence in all of them, so that is just the Comocat and the high temperature field. So that means that we can be almost sure that we have, what we see is something from the outside absorbed dichroronylane. But of course, we saw in the TEM that we have something inside as well. But now what we want to see is where the luminescence is coming from. But we had the information that in solid state we have no fluorescence because the multilaser Raman, from the multilaser Raman measurements. But in the suspensions, you definitely have a green fluorescence, and the green fluorescence must come from the dichroronylane. Now, there can be two explanations for this difference. The solid state, when you have bundles, you can contain metallic tubes and they quench the photoluminescence. That's always what's been said. Or the suspension is somehow different. And we have to see what we really measure. And what we did was, this was a smoking gun experiment. I have to explain this a little bit. The way you measure the photoluminescence in suspension is that you add some surfactant to the nanotubes and try to make such a micelle, which you can put into an aqueous solution, which will now soluble in water. The way you do this is you do a sonication in a surfactant, some mild sonications, mind you, and then you do centrifugation, and then you have some kind of sample where you put where on the top you hope that you have a lot of these micelles, and in the bottom you have the bundles. So you take the photoluminescence of this top part of the suspension, and then what we did is we filtered the whole thing. The nanotubes remained on the filter, And we did the photoluminescence to the filtrate to see if there's anything dissolved in the filtrate which is giving us the photoluminescence. And so what the result is the following. You do your photoluminescence maps, which is just coming from the, you excite to the second excitonic level and you detect the first excitonic transition and see the photoluminescence spectrum. This is the characteristic of the nanotubes. Okay, so with any excitation line, with some chosen excitation lines, what we see is that we have the suspension where you have nanotubes, and then in the filtrate, the green one, you don't have nanotubes. Okay, that's the only thing what you have to do. And then you compare the dichronoline photoluminescence. And you see that you don't have to have nanotubes in your solution in order to get the photoluminescence. So what you have is, you basically, you dissolve the dichronoline from the surface by the surfactant, and you see that. Okay, but you can still see is that our pictures are not as nice as the Japanese, but that's what we had. We have your washing solution. The first time you wash your material, your nanotubes with sodium dielectric sulfate, you get a pretty much luminescent solution, and then you keep washing, and then after a while you get a totally clear solution. So basically washing off whatever is on the side. Means that the photoluminescence in this case is not coming from the nanotubes, but it's coming from the dissolved dichronoline. And that's why I say that, you know, in material science you always have to be very careful. I have 3 more. Okay, now, what can you do? Once you have these special nanotubes which were filled by the supercritical CO2 method, it means that you have nothing on the outside, because you don't have dichronoline, and the chronoline you can wash away because that's a pretty much soluble material. Then you can now you can take the Raman spectra, and now you can see the Raman spectra from the inside, from the molecules on the inside. And, but the ultimate proof of the filling is then to heat everything up to 1250 C and convert them to double wall nanotubes, where this is in the Raman spectrum, this is a so-called radial breathing mode. This is the frequency of this is inversely proportional to the diameter. So as soon as you have this peak here, you can be sure that this comes from, if it's a higher frequency, it comes from a smaller diameter nanotube, and you have your inside, you can basically have your inner tube. So this is the Raman spectrum, but what we did here was we started from this filled nanotube, but we didn't see anything, and then we heated it up to several temperatures, okay? So 500, 700, 900 C, and we see now how a little bit we can follow the kinetics maybe of the formation of the inner tubes, and you have in the middle you have something which is very close to these polymers from the nanotubes. You see the polymerization step, and then you see some disorder. This is the deep band, which is very typical for disorder structure, and then after disorder structure, then you can and you have your inner tubes developing. Okay, so this is now the picture of it, and you can actually follow this just by following your microscopy images with time, because if you now increase the kinetic energy just by irradiation with electrons, then that's a very analogous process. And what you can see is that these are the first steps of the polymerization. You just get a little more disorder here, and you get a disordering, and then you get a slow coalescence, and there might be some kinds of steps in between. And I have to get a little personal here because I just love these images. I think that this is something which really made it worse for me to become a scientist, because we were doing this, we're trying to think about it, how this transformation can happen. And I sketched something on the blackboard, and I said, okay, this might be it, this should be very fine, but we will never have a way to look at it. And thanks to Andrei Klobistov and his TM pictures, we really can see the molecules now. So I think this is absolutely fascinating. What is practically important from this is that what we might do is at some point fine-tune this transformation, find a method with at a right temperature and right treatment of the tubes to really have these carbon nanoribbons inside, and that would be a really very important step for the planned formation of graphene nanoribbons. Okay, I just want to acknowledge my whole group. Basically, everybody took part in this, almost. I don't now cannot point to anybody because everybody was working on this project. It's just accepted. And I have actually my sincere talks to Professor Andrei Klobistov and Dr. Tom Chamberlain at Nottingham for the TEM images. And thank you for your attention.